So last time we were dealing with local extrema or relative extrema. So now we're going to look at absolute extrema. It was a problem type we saw in Calc 1. So of course we're just going to start by reviewing exactly what that means for Calc 2. So just peeking at what this looks like on Desmos. So I'm going to kind of give us what the graph looks like, maybe kind of give us the answer at first, and then we're going to work through the algebra of how to actually find that answer. So it says, consider some function f of x. And now the only thing that makes this different than what we were doing last time is it says on the closed interval from, make this a 0. We'll go from 0. Change that, we'll make it 0 to 3. So what that means graphically is we're going to graph this function on the window from 0 to 3. It turns out if you restrict a function to live within a certain window, then we have that extreme value theorem, which says you are now guaranteed to have an absolute maximum and an absolute minimum. So investigating this sketch here from 0 to 3, there is an absolute maximum. That's the highest point on this curve. And there is an absolute minimum, the lowest point on the curve. Now, this point here is a critical number. This is going to be a local minimum. But notice your absolute maximum doesn't have to be a critical number. So in Calc 1, we always said, find the critical numbers. Those are going to be candidates for what could be the absolute max or the absolute min. But then you also want to check the boundaries, because the boundaries of this function could have the highest point or the lowest point. So for instance, just because you have a local maximum doesn't mean the graph, eventually comes up and has one at the boundary over here. And it very easily could be, yes, that maybe your relative minimum is your absolute minimum. So it's still just a candidate. So step 1 is to find the critical numbers between 0 and 3. So to find the critical numbers, take the derivative. Set the derivative equal to 0. So we can see that we found a critical number between 0 and 3. Now it's going to happen where you can find critical numbers outside of the window. Like you could have found a critical number of -4. Just disregard it. It doesn't matter. We're only considering things that live in that window. So it turns out we don't actually care if this is a max or a min. We just care that it's a critical number. So to figure out the absolute maximum, all I want to know is of these 3 points, 1, 2, 3, which one has the highest y value, and which one has the lowest y value. That's it. I don't care if it's on the boundary. I don't even care if it's a critical number. So what we're going to do is just check the y values. F of 2 means the y value at 2. And then I'm going to check the boundaries, which was f of 0 and f of 3. Then we can just take 2 seconds, whip out our calculator. I'm actually going to show us a convenient way to graph this. Okay, so to graph this on Desmos, we can type, f of x equals, just like it appears on the page. And then to add that restriction, that's when we put those curly brackets. And we can say x is between 0 and 3. My step right now is I now want to plug in 0, 2, and 3. What I would recommend doing is insert a table. So you could just type the word table, T-A-B-L, and then the second you hit the E, it auto-populates the table. Go ahead and just put the x values, 0, 2, and 3. And now when I change the y values to be f of whatever is in the x sub 1 column, it's going to go ahead and plug it in. So instead of manually going in and typing in all those values, or very similarly, even if you wanted to do f of 0, f of 2, it's nice to just have everything in one nice, clean table here. So I get f of 0 is 5, f of 2 is 1, and f of 3 is 2. So if we didn't have the picture yet, and I'm looking at just this information, say it. Is the what? Is that the absolute max or min? That's the absolute maximum. Of this entire list, this has the largest y value. We don't care about the x values. Has the largest y value. And this right here is the absolute minimum.
And then graphically, you can even look at the graph and then
maybe this isn't a multiple choice where we don't have Desmos. So we would be responsible for understanding algebraically.
Yeah.
So yeah, let's glance back at the graph now. And the algebra says that f of 0, or if you want to think of this as the coordinate 0, 5, (0, 5) is the absolute maximum, and that is exactly what I see in my picture. And 2, 1 is the absolute minimum. So this is just a review of Calc 1. Again, find the critical numbers, take the derivative, set it equal to 0, just like we're doing last time. Inside the window. It's going to happen where you get critical numbers outside the window, you can disregard. Now, you don't actually care if this point is a max or min. Because when we end up putting it in the table, you're just checking the y values. I don't care if it's a maximum or minimum, no second derivative test needed.
So, do we start at like x equals 2 and go to 3?
So you're going to check x equals 2,
Okay.
and then check the boundaries. X equals 0, x equals 3.
Is there a reason why we didn't do 1, or is it just?
Because 2 was a critical number.
Okay, so whatever the critical number is where you're starting at.
Yes.
Okay.
And you can have more than one critical number. All right. just to review Calc 1, do you have any questions or want to see another example before we extend this to Calc 2? I'll give you guys a second to write that down so I can erase it. Calc 1, we're given a function, and we're given some sort of restriction. And it says only graph that function between 0 and 3. So now in Calc 3, we have some sort of surface, but we're going to be bounded by, and it will give us a description of some sort of region in the xy plane. So this surface doesn't go on forever. It's saying we're only going to live in a certain region. So step 1, just take a second and actually sketch the region that they're describing, just so we understand exactly what we're looking at. Most of the time, these will be pretty straightforward. They'll be straight lines or circles or something pretty straightforward. If they're not, we've got Desmos. We can go ahead and sketch what these things look like. So I have x equals 0. That's my vertical line. X value is 0. I've got y equals -1. So horizontal line with a y value of -1. Then I have y equals 3 plus x, or x plus 3. That's a line with a y-intercept of 3 and a slope of 1. So this is the region that we are graphing our surface above. So again, this is the xy plane. And we're saying only consider this surface bounded by this region in the xy plane. So this is I'm in Desmos, I look at my bird's eye view, and the surface will only live just above this triangular piece. So let's actually talk about how to graph this in Desmos. So I got Desmos 3D now. Just type the surface in. So this is the surface that they gave us. I see a nice parabola. I'm just going to go ahead and play around with the window a bit, just to make this a little cleaner. Maybe make this -3 to 3. And then y values from -1 to 15. Just so I can see this area a little better. So now on the next line, I'm going to say sketch f of x comma y, but sketch it with the restriction. So this is actually what we just did in Desmos 2D. I want to sketch y values from -1 all the way up to this y value of 3 plus x. So I can tell Desmos to sketch this between -1 to 3 plus x. And now sketch the x values from here to here. Let's go ahead and take 2 seconds. I'll put that in a different color. And actually identify those vertices of that triangle. Some of them are going to be pretty easy to spot.
X is -3.
Same?
X is -3.
This one?
No. What you saw for the 3 plus x one.
And you said it was what?
I think -3. I just
0, 3?
3 so 3. Okay.
Because of the positive ones. So like I said, some of them will be easy to spot. 0, 3. This is an x value of 0, a y value of -1. So 0, -1. This one I know has a y coordinate of -1. But to find the x coordinate, I could just set this equal. I could say, when does 3 plus x equal -1 when x is -4? So now I'm going to tell Desmos to sketch this from x is -4 to x equals 0. So I got a second brace, -4 to 0 for x. And now ready? If I look at my bird's eye view, let me change this x to
What it is.
-4.
Bang. Good ear.
So this is the exact
Nice.
triangular region that we sketched. And it's in blue, showing only sketch that. So now here's what we're doing. We are no longer interested in everything outside of that region, so just turn it on. This is now the region that we want. So just like for our Calc 1 example over there, we had that entire parabola. Well, we said we're only sketching it between 0 and 3. We have the entire surface, but we're only interested in the surface bounded by this region. So again, this is our bird's eye view. If on Desmos I hit my bird's eye view, then I see that region. Please ask questions about just the graphing and understanding the region before we try to find. Now we can see this has an absolute maximum. This has an absolute minimum. The minimum could be a local minimum inside the region. The maximum could be one of the vertices of the triangle. And the maximum could actually be along the boundary. Maybe this piece kind of, jets upwards like that past the vertex of the triangle. So it's going to be a little tedious, but we have to check inside the region, using our local extrema from last time. The only new piece for us is we now have to check along the boundaries for any extrema there. Alright. Feel some confidence. Step 1. Find. So I'll put steps. We want to sketch the region in place. So step 2, find the critical points inside the region. I'm going to remind us there's no need for the second derivative test. I actually don't care if it's a local max or local min. We're going to do the same idea, just look at all of the y values at the end and just see which one has the largest bracket. So I'll give you guys a second to practice from last time. Find the critical numbers. Take the first partials, set them equal to 0, solve for your critical points. So I found a critical number, -1, 0. So I'm going to go up to my sketch. And label that point. Now, our note here says the critical points inside the region. If I were to find some point like 7, 4, no need to even worry about it. Just throw it out. Same thing over there. If you found a critical number outside the boundary, we don't care. So our candidates for being an absolute extrema here is going to be something inside the boundary. That is what step 2 covers. Finding any local extrema is going to be everything inside the region. And we only have one candidate that we need to check inside the region. Now we need to check things along the boundaries themselves. So I'm going to run over here. And if you want to add to your list of steps, add a step 3, which is to check the boundary. So we say find extrema. So looking back at our picture, labeling is going to be super important. This is the line y equals -1. So we're going to check everything along the line of y equals -1. Then we're going to check everything along the line x equals 0. And then we're going to check everything along the line y equals 3 plus x.
Okay. See that.
Let's do x equals 0 first. I think that'll be the nicest example. So I want to check everything along the line x equals 0. So just showing that in Desmos. So this is my region, and in green I've got this x equals 0. And I'm just showing us that along that boundary, you are going to get some sort of trace of a 2D curve. That will have a min or max. So what does that look like algebraically? I'm going to rewrite the function up here. I now want to plug in x equals 0. So that's our notation, f of 0 comma y. It's saying plug 0 in for x, but then just keep the y. So plugging that in, I've got 0 squared plus 2 times 0 plus y squared plus 3. And now this will clean up to be a single function in y. So just to make this look as simple as possible, I'm just going to call this some new function of a single variable g of y. Just so that this looks like a Calc 1 problem. If you look at it, this is a function with a single variable. Calc 1, this would have been easy breezy. And you just want to find the extrema along that boundary. So find the critical numbers. Take the derivative, set it equal to 0. Now, organization is going to be the biggest thing here. I found that there is a critical number at y equals 0, okay? don't forget our kind of header up here, we were plugging in x equals 0. So if I was plugging in x equals 0, and I found that y equals 0, that now describes the point 0, 0. What does that mean? Coming over to my sketch over here, this is going to be like a master sketch, by the way. By the end of these problems, you're going to be looking at this drawing a lot. So in step 1, sketch the region. Maybe you want to put something like, spend some time making it an accurate picture. So now, along this line, I have the point 0, 0. And I'll show you in Desmos exactly why that point is important. Along this green line, x equals 0, we are saying that the point 0, 0, whatever you get when you plug it in, is going to be a max or min along this boundary, and you can see it. Along this line, you have a minimum. So now let's go ahead and do y equals -1 together. So I've got f of x, comma, I'm letting y be -1. So all my x's stay the same, and y is going to be -1. And now, I've got some nice, clean function in terms of x. So I'm just going to call this some new function g of x. Again, now you want the max or the min along this line. So go ahead and take the derivative, set it equal to 0, and now just stay organized. This means I have the critical point -1, comma,
-1.
-1. Stay organized. When you're plugging in a boundary, write it at the top. You're going to work all the way down. You're going to get the other variable. Go back up to the top. Now we got to include that in our drawing over here. That was the point -1, -1. So now, the last thing for us to check is whatever this line is, which is the line y equals 3 plus x. So take 2 seconds. Now, every time you see a y, you're just going to plug in 3 plus x. Clean it up. Write it as a single function in terms of x. Find the critical numbers. So you could have FOILed this out. You also could just use chain when you go to take the derivative. Drag the power down, subtract 1, just don't forget to multiply by the derivative of the inside. But lucky for us, derivative of the inside is just 1. So now we want to set our derivative equal to 0. So I land on x is -2, go all the way up to the top. It's not always going to be a number. No worries, you can just plug -2 in. And y is 3 plus the x coordinate, which is -2. So 1. So now I just come over here. I've got -2, 1. So now you want to check all of the candidates. All of the candidates, now everything in blue is a candidate. All of the critical points, that's everything inside the boundary. The points along the boundary, that's what we did. We were checking each of the individual restrictions. And then lastly, the vertices are actually candidates too. 0, 3, 0, -1, -4, -. So again, it would take forever if we sat here and plugged 0 in for x, 3 in for y, and wrote it down. So we want to go ahead and get a table going in Desmos. For Desmos 3D, it works out the same. If you just type in table, you can type in the x, which I'll do 0, 0 first for simplicity. And now just go to this third column over here. And now you can just say, what is f of x sub 1, y sub 1? Boom. And it plugs 0, 0 into the function form. So now all you need to do is just carefully look for all of your candidates and plug them all in. So the last thing we're going to go ahead and do, and we should probably do this honestly as we find them, is have a nice, neat table. And every time we located a candidate, yes, you're going to mark it in your picture, but then you're going to go ahead and include it in this table up here. Well, right here is the projected one.
No, you're here.
So I'm just going to write down all of the critical numbers that I see. All the candidates, I should say. -4, -1, -1, -1, 0, -1, -1, 0, 0, 0,
-2, -1.
-2,
Positive one, I'm sure. So you have a total of 2, 4, 6, 7.
just plug these into this. So just for cosmetic purposes, I'll show you. Once you have this table, you can just say graph the point x sub 1, y sub 1, f of x sub 1, y sub 1. And it will graph all of your candidates for you. So if you go to the bird's eye view, that's actually what we see in our 2D picture over there. I see all of my different candidates, the vertices, the points along each of the boundaries, and the critical numbers inside. If I kind of make this a 3D perspective now, these are all of the different candidates. And you can just check. I can go up to my table, and let's go ahead and actually fill in the values. 12, 3, 4, 2, 3, 4, 12. The absolute minimum, or the smallest y value, is this point. The absolute maximum, it can't happen where you get 2, because they have the same y value. So just to reduce clutter, I'm going to go ahead and turn off this point, and I only want to graph the absolute min and max, -1, 0, 2. And you can see on this entire region that we have, that is the absolute lowest point on the surface. And for my absolute maximums, -4, -1, 12, and 0, 3, 12, those 2 points are tied for the absolute maximum. So then the last thing we want to do is just identify absolute max, absolute min. The absolute maximum is both -4, -1, 12, and 0, 3, 12. And the absolute minimum, -1, 0, 2.
So in that case, you, both of them are the absolute max.
Yes. So there's kind of a lot. There's definitely a lot to it. So we're going to go through exactly what we did one more time to help the whole kind of story stay together. The actual prompt is to find the absolute extrema, so absolute max, absolute min, bounded by, and it gave me a region. Step 1, sketch the region. This is now a region in R2, so I'm just going to sketch x, y axes, and sketch x equals 0, y equals -1, y equals 3 plus x. You're going to see some sort of bounded region. It could be a triangle. It could be a rectangle. It could be a circle. It's some sort of region bounded in R2. I think triangle is the easiest example because you only have 3 things to check. But rectangles are fair game. So sketch the region in R2. Make it a nice, clean sketch. Because as we see, you're going to be labeling points along the way. So make sure, try to draw things to scale, try to draw things straight, neat, if possible. Find all critical points inside the region. That's just what we did last time. You find the first partials, set them equal to 0, find critical points. There's no need for the second derivative test. When we throw everything in a table, I don't care if it was a local max or local min, just not relevant. So once you found a critical point, put it in your sketch, put it in your table. Now you want to check everything along the actual boundaries. And in our nice clean sketch, we labeled this is x equals 0. This is y equals 3 plus x. This is y equals negative 1. So then we want to check y equals negative 1, x equals 0, y equals 3 plus x. For y equals negative 1, just plug in negative 1 for y. And now you get a function in terms of only x. Now it just turns into a Calc 1 problem. Take the derivative, set the derivative equal to 0, find the x value. Well, if x is negative 1, then y was negative 1. So I have a new candidate, negative 1, negative 1. So once you do that for each of the equations of the boundaries, you're going to get critical numbers along each of these points. That goes in your sketch and in the table. Lastly, go vertices 2. Negative 4, negative 1, 0, 3, 0, negative.
For these kinds of questions, will we be given the bounds? Like, will we always be given the bounds?
When you say the bounds, do you mean like these equations here?
Yeah, like the y equal, yeah.
Yes. So the first thing we're probably thinking is, there's no way this is a test question. So it is, but maybe you're thrown somewhere in the mix. Maybe I give you the region and all the candidates, and you just check for the absolute max or min. Maybe I gave you all of the candidates except, and I think the way I did it the last time I gave an exam was I did something like this. So all of the candidates were marked, but you knew that you had to find this point and this point. So on the exam, I will never ask you from start to finish to do the full problem. There's just simply no time. But if I threw you in halfway and said, find the absolute extreme along y equals negative 1, you could plug it in, get a critical number, find the time. So then lastly, you have a table. Don't do it by hand. We'll be sitting here all day long. Just make a table in Desmos, type in the values. Lastly, just identify what is the largest value, that's your absolute max. Sorry. Largest y value, that's your absolute max. Smallest y value, absolute max.
And you saying y, is that your z value or is that the smallest?
Thank you. Smallest z value. I'm stuck in Calc 1. You find your smallest z value. All right. It's called number 2 because what we just did was actually the answer to number 1. So the solutions will be posted on Blackboard. So you've got a nice clean example to look at the practice problems. We're still going to do, excuse me, we're still going to do 2 together, but I want to slowly but surely make sure we have all the steps. So step one, just graph the region in R2 and in Desmos. So I want to make sure that we can graph this neatly in Desmos so we know what this looks like. Man, that took almost an hour for one problem. So if it writes it in an inequality like this, it's saying x is between -1 and 1. So between the lines, x equals -1 and x equals 1. So you're going to sketch both x equals -1, x equals 1, y equals -1, y equals 1. And the best way to see it is hit that right for example. Now zoom out a bit. And you do get that square if you look at that. Maybe just change the -2 for just x of 1. we all have the picture in Desmos. So I have my surface, but I only want to think about it on that region. So I'm just going to turn on the other piece. I've got a closed surface. If I go to my bird's eye view, I should see that nice square. -2, -1 to 1, -1 to 1. So again, just making sure that we're staying organized along the way. I'm going to go ahead and, in my sketch, in my 2D sketch, I know, sorry Reginald, I'm all over the place there.
That's okay. It's okay. Just trying to keep up. That's all.
So now just make sure we're staying on top of it and identify all of the candidates as we go along. This would be the point, one more. This is the point 1, -1. -1, -1, -1. So those are just going to go right into my table up here. So step 1 says sketch the region in R2, check. And I can clearly identify the region that I'm interested in. It's this region in here. Now I want to find all critical numbers or critical points inside the region. So just lesson from last time. Find your partial derivatives. Set them both equal to 0. Looks like over here there is a 2x in both terms. And now I want to plug these in over here. If I plug in x equals 0, I get y equals 0. If I plug in y equals 1/2, I get plus or minus √2. Now something that I want to be super clear about, you need an x and a y. But what you can't do is say, oh, I have the point 0, 1/2. Because this is only the partial derivative with respect to x. I need a coordinate that makes both of them equal to 0 at the same time. So I need an x from here and a y from here. Well, if x equals 0, then y equals 0. So that's one of my critical numbers, 0, 0. If y is 1/2, well, if y is 1/2, I get plus or minus root 2, which means that is the coordinate square root of 2 comma 1/2 and negative square root of 2 comma 1/2. You've got 2 points there. Please ask questions on just the critical points. Sweet. Someone tell me, what is square root of 2 as decimal?
1 point something.
1 point something? Yeah.
1.6.
Why is that relevant for us here?
It's outside our boundaries.
It's outside the boundary. We're only living between -1 and 1, -1 and 1. So square root of 2 in the calculator is 1.4-ish something. Oh, well, what that's saying is go to 1 point something, and then, well, I don't care. I'm already outside. So we do not need to consider this. It's going to happen where you get critical numbers that live outside the boundary, and even if you were to check this line here, x equals 1, you could get the point 1 comma 6. True, it lives along x equals 1, not inside the region, so I don't care. It's going to happen, you just disregard it. It does not go in your candidates list. But 0, 0, which does live inside, is a candidate and goes inside our table. Any questions so far? Sweet. All right, for the sake of time, we won't have time to actually check y equals -1, x equals 1. But I want to walk around and make sure that we can enter the table into Desmos, and we can have it plot the points just to see how we're doing. So just making sure that we're all on the same page for Desmos. Go ahead and now enter that table into Desmos. You're going to want to enter a z for g of x sub 1, y sub 1. And then, just for exercise, I'm going to have it plot all of the candidates that we have so far. These are not all of them. And now, if you want to look up on the projector for a second, you'll see why checking the boundary is actually important. So I've checked the vertices, but notice that this line, which would be y equals 1, if I were to spin around and show you, that is actually not the highest point. This curve kind of dips upwards. So whatever this point that you find along the boundary will actually be the maximum along that line. Now it doesn't end up mattering since it's not going to be the highest one, but still, nevertheless, checking those actual lines is important. so I will let you guys finish up number 2 over the weekend. The solutions will be posted to Blackboard, so you'll be able to check, see how you're doing. When we come in on Monday, same thing. It's a huge problem type. It's very time consuming. So when we come in on Monday, we'll continue to practice. Maybe just look at some more interesting regions, like what if it lives inside a disk, and things like that. Any questions? All right, everyone, have a good weekend. I'll see you Monday.
That one problem from yesterday with the natural law. Are we going to go with E? Or do we use the natural law on that one to get rid of the E? This one. Then we have to set it to 0.
Oh, yes.
Are we using the law of E to get rid of the natural law to get rid of the E?
So it turns out e to the anything will never equal 0.
Right, yeah, that's because natural law, you can't take natural law, so you can't take natural law on both sides.
And if you thought about this graphically, e to the x is like that. And e to the x equals 0 is saying when does this cross the x-axis? Never. It gets close.
Okay, right, and it gets, infinitely close, but it'll never cross.
So when you're solving things that look like this, and you set each of the factors equal to 0, when you see e to the x, e to the something equals 0, that never happens. You only have to solve this one.
Okay.
Now, to be clear, if you have e to the x minus 2 equals 0, different story. Because now you have e to the x equals 2, which does happen. But if you get e to the x, e to the something equals 0.
Yes. And since it's time, it's not like a minus or a plus. Okay, so you take it to the other side.
And exactly like you said, when you take the natural log of 0, you can't do it.
Can't do it, yeah. That's why I was like, oh, don't erase that.
All right.
You know, I'm gonna finish. I'll erase it, because I want to remember it. Okay, yeah. Take a little screenshot. Thank you. So I was definitely wondering about that. It's getting clearer. Guess the second time around means something.
No, I mean, that is how it is.